There we go. So we're back on lesson 3 out of 3 in the R for SAS users curriculum, which is about my very first generalized linear mixed models. So we've gone from just working with data and to doing some linear models, linear mixed models that have random effects. And now we're going to do generalized linear mixed models, a very powerful and flexible tool for analyzing data. And we'll talk about what exactly generalized linear mixed models are as we go. So a disclaimer here is that in the previous 2 lessons, all the numerical results of the R and SAS code were identical. You could verify them against each other if you wanted to. I still provide SAS code for these lessons. However, the results are no longer identical, and that's because some of the sort of default model fitting algorithms for these type of more sophisticated models differ between R and SAS. It is possible to get them to agree exactly if you tweak a bunch of settings, but I felt that that would be sort of detract from the learning purposes here. So we don't get exactly the same results in between R and SAS here. Numerically, they're slightly different. If you're really interested, I can go into that in more detail, but yeah, I just wanted to note that. So the learning objectives for this final lesson is to learn what generalized linear mixed models are and what kind of situations they are useful in, and learn more about, we've done a little with using models to make predictions, the estimated marginal means. We'll keep delving into that, and we'll also look at how to fit mixed models with more complicated covariance structures than what we have been dealing with so far. This would be something for repeated measures situations. Again, we are going to do sort of the pipeline, starting from the data import to exploring the data, fitting the models, and getting some results. And the same, we're going to use a new worksheet from last time, the 3rd worksheet. And I'm about to go back into the RStudio server and get things going for lesson 3. But I just want to mention that, as usual, the first thing we're going to do is load our packages. We're using some of the same ones as last time, but we're using, I mentioned these already, I think today. GLMMTMB is a mixed model fitting package that has a little more complexity than LME4 and lets you fit different classes of model with different error structures than we have had to do in the past. So that's what we're going to use this time, GLMMTMB. Dharma is a good package for, we've been using check model to make from Easy Stats package to make our residual diagnostic plots, but you can get more appropriate diagnostics for generalized linear mixed models using Dharma. I won't go into the details of it too much, but that's what we're going to use for that. And we're going to set our plotting theme as usual. So let me go to the RStudio server, and as before, because we're starting from scratch again, I would recommend clearing the objects from the workspace. We'll go ahead and delete them with the broom button as we did before. And also let's go ahead and restart R to start from a clean slate. It's not necessary, but it's a good idea. And I'll close this worksheet, clear away the output from before. And so the thing you really need to do, though, is go to the Files tab on this lower right pane, click on Files there, and then open up the Lesson 3 worksheet. So here we are on Lesson 3. And the first thing we're going to do is highlight the code to load the packages and set the plotting options, and then we'll go ahead and run that code. Hit Control-Enter to run this entire block of code. And as usual, warnings and messages pop up, but everything loads as it should. we're going to work with two example data sets in this lesson. The first one is called CBPP. It comes preloaded with the LME4 package. CBPP is apparently a respiratory disease of bovines, and it was in this particular data set. It was studied in herds of zebu cattle in Ethiopia, and they whoever collected this data surveyed a bunch of cattle herds, 15 of them, and in each herd at each time point, they did this at 4 time periods. They counted the total number of cattle in the herd and the total number that had this disease. So we sort of have our data are binary. It's yes or no. Like we looked at a bunch of cattle and said, does this one have the disease? Yes or no. And for some reason, period is the factor, the fixed factor that we care about determining if these 4 time periods have significantly different levels of disease averaged over the different herds. That's our scientific question. Yeah, so this is how you import it in SAS because it's not a built-in data set in SAS, but because this is a built-in example data set in R, we don't have to read it in from an external file. We can just use this data function, which loads an example data set into our workspace that comes with one of the packages we have loaded right now. So we're going to do that. We're going to use the data function. Yep, hit Control Enter on that. And now it's sort of a promise, which means it has not yet evaluated, but the example data set is now available for us to use. Now I'm going to use the glimpse function to look at the structure of this data. And we'll talk about what's in it. So I'll change this to glimpse. Hit Control Enter to run that. So you can see it is a pretty small data set. It has 56 rows and 4 columns. The herds are given numerical IDs, and you can see this is already set as a factor variable. So we have these are just IDs saying which herd each observation comes from. Incidence is the number of cattle that had the disease when they were surveyed, and size is the total number of cattle in the herd, including those with and without the disease. So in the first time period, and time period is also a factor, even though it's a number, we're treating it as a discrete factor here. Like in herd 1, in time period 1, 2 cattle had the disease, and there was 14 total cattle, so 2 and 12. So far, so good. The next thing we're going to do is plot the data. We want to look at whether the herds seem to have any trend over time in their incidence of the disease. And so we're going to use our X variable in the plot is period, time period. And the Y variable is incidence divided by size. It'll be like a proportion between 0 and 1 of how many cattle had the disease at that time period in that herd. And we'll make a line plot and we'll group it by herd, which means we're going to make a separate line for each herd. So let's do that. So the X variable is the time period. The Y variable is incidence divided by size. So that's the rate of disease. And the group is herd. Which herd does, we'll see a separate trend for each herd on this plot. So here's what it looks like. Nothing too amazing stands out here. We see that maybe the average incidence of disease kind of goes down as you go to time period 4. And some herds have different trends over time. This herd went up and down. This one went down and up. It's kind of all over the place. And sometimes a lot of herds had 0 disease on many days. or time, whatever the time periods are. Okay. We know already from talking about mixed models that we cannot just throw all this data into a model without accounting for the fact that measurements from the same herd at different times are not independent. Those are the same cattle measured on different days, and so they might, one herd might be more prone to disease than another. So multiple measurements on different time periods from the same herd are not independent. We have to account for that correlation by making herd a random intercept in our linear mixed model. And so what if we just go ahead and do that? Well, we've got a linear mixed model. The response variable is the proportion of cattle that suffer from the disease, the incidence divided by size. Time period, our fixed effect, discrete, looking at 4 discrete time points. And we have a random intercept for each herd. That should do the trick, right? So and we call it LMM CBPP, the linear mixed model fit to this CBPP data set. So incidence divided by size is our response variable. Period is the fixed factor. And 1 type herd means a random intercept for each herd. Control Enter to fit the model. Okay, it fit. What do we do next? Let's look at the model diagnostic plots using the check model function. Check underscore model. We see, you don't always get perfect diagnostics with a small data set, but it's really not terrible. There's the residuals are all kind of on a straight line, and they're not too far off the normal line and that kind of thing. So we're not too displeased with the model diagnostics there. But now let's look at we have, a bunch of cattle that we said either you have the disease or you don't. And what we want to estimate is average across all the herds. What is the model's estimate of the proportion, the probability of a individual of these cattle having CBPP and its confidence interval at each time period. So we'll use the EM means function to get the estimated marginal means from this model by time period. EM means by time period. Okay, and here are the estimated marginal means for the 4 time periods. As you can see, just like we saw from the raw plot, they sort of go down over time. The average, the probability, the model estimated probability of having the disease across all herds at time 1 is about 22%. Then it's 7%, and 9% goes down to 4%. And these are the 95% confidence interval lower limits of those estimates and upper limits. So can anybody tell me anything that might be an issue with these 95% confidence limits? Anyone have anything they think looks wrong to them about that? This is a test to see if you're still paying attention. Yes, Josh.
Is it that the 95% is ultimately arbitrary? The threshold?
I mean, it is arbitrary. Yes, I would agree with that, but that's a good point. Obviously, 95% is based off of this decision rule of alpha equals 0.05, which is arbitrary. But the thing that I was focusing on here is that a probability only makes sense if it's between 0 and 1. Probability can never be negative, and it can never be greater than 1. That doesn't make it, you can't have a negative probability of flipping heads on a coin or a probability greater than 100%. And we see that this confidence limit here in particular is negative. So that means we sort of there's 95% confidence that the value of the probability of getting the disease at time 4 is between -3% probability and 11% probability. That doesn't make any sense, right? It's a nonsensical statement. And the reason that we get this statement is because we were assuming normally distributed error, and that isn't necessarily a good assumption if we're dealing with binary outcomes with probabilities, because normal distribution is a bell curve. It goes out infinite in all directions, but probability can only be between 0 and 1. So normal distribution is not necessarily a good distribution to look at the error when it comes to probability, because probability cannot go out in all directions like a bell curve. So what are we going to do about that? Well, again, because these mean proportions, we can't assume that the error around them is symmetrical and normally distributed. We're going to use a generalized linear mixed model to look at probability on a different scale and compare it. I'll explain what this means in a second. So basically, what the GLMM does is it uses what's called a link function to basically take the scale of the of our predictor variables and convert that to a scale that corresponds to our probability. So take our combination of fixed and random effects, which can be anything, positive or negative, right? And then translate it to a 0 to 1 scale for probability. And then we sort of fit that model, and then after you're done, you undo the transformation so that you can interpret the model means and confidence intervals back on the original scale. So how does that work? Well, like I said, the response variable in this model is binary. For each individual in the herd, we either have a 0 or a 1. It's either 0 means it's healthy, 1 means it has the disease. Our model is trying to predict the probability that a randomly chosen animal from a given herd at a given time will have from an average herd at a given time will have the disease. That has to be a number between 0 and 1. It cannot have normally distributed error, because if it was close to 0, that bell curve would go into the negatives. And if it's close to 1, the bell curve would go above 100% probability. And so here is I didn't want to show too many equations in this, especially late in the day, but this is the formula for the probability of disease for the individual I in time period J in herd K. It's an intercept plus the fixed effect of the time period plus the random effect of herd. Okay, that's overall intercept, fixed effect, and random effect gives you, it doesn't just give you it gives you the logit of the probability. But I didn't explain to you what logit was. So what does that even mean? Logit is the link function. Logit is a function that translates a probability, which can only be between 0 and 1, to a scale that can take any value, positive or negative. It basically transforms a value p, which can be between 0 and 1, to a log odds scale. And yeah, this is the function. It's just log of p divided by 1 minus p. This can, even if p is only between 0 and 1, this value can be anything, positive or negative. And this is what the logit function looks like. If the x-axis is the probability between 0 and 1, the y-axis is the logit of the probability. It goes between, well, my plot goes between 5 and -5, but you can see that this line keeps going up. It goes all the way to infinity. You can see that here in the middle, it's about a straight line, but then it never reaches, it never passes 1, it never passes 0. It just curves and goes up. And the way you could interpret that is like, if you have an event that has an extremely low chance of happening that's close to 0, and you increase the probability of that a little bit, that'll increase the odds a lot. It's like, if you eat a certain food, it can decrease the odds of you getting cancer by a factor of 10. But if your probability of getting that specific cancer is already very low, that changes the factor of the odds by a lot, but it only changes the probability a tiny bit. But so that's why it's the line is very steep there. But if you have a 50% chance of getting a disease and you eat a food that makes that odds go down by a factor of 10, that will make the probability go down a lot. So it's like if you already have a 99% chance of doing something, you can't really increase that very much more. So there's almost nothing you can do to make the probability go up anymore if you already have a 99% chance of the thing happening, right? And same thing with if it's near zero, there's nothing you can really do to make it less likely to happen because it's already almost zero. You have the most leverage when you have a chance near 50% of something happening. Does anyone have any questions on that or need clarification since it's a bit confusing? The reason that we care about this here is because we are using it to take our 0 to 1 scale and translate it to a scale that we can fit a statistical model on, which is the scale that can be any number, positive or negative. That's why we're using this function here. And this can be done in SAS with proc-glim-mix, and dist equals binomial. Binomial distribution is the distribution of outcomes that are binary, 0 and 1. So that's how you would fit the binomial generalized linear mixed model here with the logit link function. And in R, we are going to use GLMER instead of LMER. And it's very similar to what we did before. Last time we had this same model formula, incidence divided by size, as a function of the fixed effect and the random effect, but we are going to have a few extra arguments. First, we have the argument weights equals size, which means the size of the herd is the sample size for the binary outcome. So like a herd that has 20 cattle is more contributes more to our estimate of the probability than the herd that has only 2 or 3 cattle. There's more coins you flipped there, so you get more information. And we use the family argument to say what is the response distribution we're going to use and what is the link function here. And that's this here. We're using the binomial distribution with the logit link that we just discussed. Family equals binomial with a logit link. That means this is the appropriate model to use if we have zeros and ones as our response data. So let's fit that model. Okay, and we're calling it GLMM now because this is a generalized linear mixed model. We're going to use the GLMER function. And just like, so we're going to use the same model formula, this incidence divided by size as a function of period and herd. Period is a fixed effect, herd is a random effect. So you could actually just copy this whole formula and paste it in here because we're going to use the same formula just to emphasize that this is the same formula as our model that used incorrect. This model has the correct formula, but it doesn't have the correct error distribution. So we're using the same formula with a better error distribution. But we have to specify this weights equals size to show that the herds have different sample sizes that are different numbers of binomial trials, binary outcomes in each one. And we're going to use the binomial family, binomial, and the link function is logit. We had to put that in quotes. And I think you had to put one more parentheses at the end since here you have one parentheses to cover up the binomial, and this parentheses is for the original function. So there should be 2 parentheses at the end. If we hit Control Enter, it will run that line. Anyone have any questions right now? Cool. So now that we have a generalized linear mixed model, we really need to use this special package called Dharma to do our residual diagnostics. And it uses a special method of generating simulated residuals and doing all the tests for normality, outliers, and whether they have constant variance. And so we're going to use this function simulate residuals, and then we can plot that, and it will tell us whether the model is a good meets the assumptions of a generalized linear mixed model. So yes, we're going to use the function simulate residuals to do that with a capital R. And then we'll plot that. So we'll run this line as well. And we see there is no, this actually gives us significance tests for the different assumptions, and they all say not significant, which is good because it means there's no significant deviations from the assumptions of the model. And you can also see on this plot, all the residuals fall along the observed versus expected is all in a straight line, which is good. And these are the variants of the different subsets of the data, and they're all about the same. There's no major difference there. So we're happy with our residuals of this model. The last thing, so this is the first of 2 examples in this lesson. The last thing we're going to do is get the estimated marginal means from this new model, and we can compare the confidence intervals from the ones we got last time to see if they are actually within our 0 and 1 bounds. And in here, we're going to use the argument type equals response, which means we want to go back from our logit scale back to the 0 to 1 scale. So do a back transformation, basically. And I also threw in this pairwise in here, which means we're going to get our contrast between each level of period all in one step and use the Tukey test to test whether they're significantly different from each other. So this does that all in one step. It's kind of handy. Instead of just by period, we have pairwise by period, which means we're going to get the mean for each of the 4 time periods and then take all the pairwise comparisons between them. So we want pairwise by period, and we want them on the response scale, and we're going to use the Tukey test to compare them. So I'll hit Control Enter and run that line, and now we see here are the probabilities. They're kind of similar to what we had before. It's about 20%, 8%, 7%, and 4.8%, which is, if you go back, that's fairly similar to what we had before. But our confidence interval limits are now all between 0 and 1. So we have they never go negative, and they never go above 100%, and that's exactly what we would want. And that means our model is giving us predictions that actually make sense. And now we have the contrasts between each pair of time periods. Now this is something that is maybe not as familiar to some of you, because we're now giving the contrast in the form of odds ratios. When you compare 2 probabilities, the appropriate comparison is the odds ratio. I think, let me show a slide about that. Oh, I don't have a slide about that. The idea is it's the number of times higher odds in period 1 versus period 2. So the odds of getting the disease is 2.7 times higher in period 1 versus period 2, and that's significantly different. But the odds of getting the disease difference between period 2 and period 3 is only a 1.1 ratio. So an odds ratio of 1 means no difference. This one is close to 1, and so it's not significantly different. at p equals 0.05 because that ratio is very close to 1. So the difference between time period 2 and time period 3, which are both around 8 or 9%, is not significant. So that is the first of 2 examples here. Does anyone have any questions before we proceed with the last bit of content for today? Okay. I know it's been a long day. I appreciate that you all are still listening. Again, if you get very bored and can't pay attention anymore, I will not be offended if you peace out of here. So the last example of this R for SAS users curriculum is now if we have both data that are not have normally distributed error, and we also have repeated measures in time. You have to do a little bit more with the random effects, not just to account for each group having a different mean, but also to account for the fact that measurements in time are more closely correlated with each other the closer they are in time. So this is a example data set from looking at how effective 3 fungicide varieties are at reducing disease in cotton seedlings. So we have 4 treatment groups in our study. We have an untreated group that didn't get any fungicide, and we have 3 different kinds of fungicide. And right, so there's 4 treatments. So there's a plot, 4 plots in a block, one for each of those for the 3 treatments in the control. And there's a randomized complete block design with 5 blocks. That means we have 5 units of 4 plots in a randomized arrangement, each of which gets a different treatment. And each of the plots had 400 plants in it. And at 3 different time points, 12 days old, 20 days old, and 42 days old seedlings, they counted the number out of the 400 that had the disease. It's a pretty simple data set. Again, the same plots were measured at 3 time points. You cannot consider the 3 time points to be independent. You have to model in your statistical model has to account for the fact that the different measurements from the same plot at different times are correlated. One plot might just have more disease because of some factor of what batch the seedlings came from or what the environmental conditions are or whatever. You don't know, but you have to model it. And because they're measurements in time, measurements that are closer in time are more likely to be correlated than measurements that are far apart in time. We have to model that as well, or we have to see if that is important. So that's what we call repeated measures. Some people call it split plot in time. So we can import the data from the data folder on the cloud server. It's called fungicide.csv. We're going to read it in and assign it to an object called fungicide in our workspace. And before we look at the data, we're going to set all our our columns that need to be factors to factors. We have a block ID, a plot within block. We're going to set time as a factor as well because we're going to consider them discrete time points. And then also, I put in this code to change the ordering of the levels of fungicide so that the reference level, the intercept in the model, is going to be our control group. So we want the intercept of our model to be the control group. That makes a little more sense when you're looking at the parameter estimates if control comes first and the 3 treatments, so the parameters are like the difference of each treatment from the control. That makes more sense. But none is the name of the control, which was not first in alphabetical order. So we have to specify to reorganize the levels so that none comes first. So we'll run this line 59 here to import the data. Fungicide. And then I didn't give you any blanks to fill in there because this is just some sort of data management here. We're going to run this block of code, Control Enter to change them all to factors. Let's take a look at the fungicide data. We can see there's well here, let me just type it into the console. It's a little easier to see. It has 60 rows and 8 columns, right? We have a block ID, a plot ID, what fungicide treatment was applied, the number of plants, which is always 400, the time point, 12 days, 20 days, and 42 days. Then they counted the number of healthy plants in each row, but we're not going to worry about row for this example. I just summed them up. Yes, this number of healthy plants is the sum of these two numbers. So like in this plot, there was 400 plants and 295 were healthy. Then at day 20, only 266 of them were healthy. So some of them got the disease. Any questions so far? So this is an exploratory plot. I prefer if you have only a small number of data points, instead of doing box plots, to just plot all the data as points and just plot the medians over top of that. To me, sometimes the box plots actually make it harder to see what's going on because you don't see where the individual data points are. So what I'm going to do is I'm going to plot them as all the data points. And we're going to use time on the x-axis, the three time points. We're going to color them in by fungicide treatment. We're going to group them by fungicide treatment, and our y-axis is the number of healthy plants, so the number that did not get the disease. And I have various things here, including a colorblind friendly color palette. And so we're going to, time is going to be our x-axis. Fungicide is going to be the color of the points. We're going to group them by fungicide so that the data points from each group are with each other. And number of healthy plants is on the y-axis. And so here's the plot. You can see that the black dots are the number of or the number of healthy plants in the treatment that did not get any fungicide, and this line is the median. So you can see that the number of healthy plants goes down over time. So the disease was developing over time, and maybe you can see that the ones that didn't get any fungicide tend to have a little bit less healthy plants, a little bit more disease than the other ones. But the fungicides themselves don't seem to be too different. They all seem to do a little bit better than the control, but there's not one that stands out as being a lot better. And let's also look at make sort of a line plot for the different blocks, so we can see if there's variation by block in how much disease there was in the different treatments, which will kind of justify why we need to do our mixed model. So this time time is on the x-axis still. Block is our we're going to color it in by block this time, and we're going to use the number of healthy plants still as the y-axis, and we're going to group our lines by block. So time is on the y-axis. We're going to color it in by block. Number of healthy plants. Yes, time on the x-axis, number of healthy on the y, and we're going to group it by block. So what do we see? Do you see any systematic difference between? So yes, this like anything that has the same color is from the same block, regardless of what treatment. Do you see any patterns when it comes to the blocks? Can anyone comment on that? if anyone's listening.
Yes, I think so.
Yes. So in particular, I would say block number 5 has higher numbers of healthy plants across all the treatments, right? So that block is maybe just the disease did not do as well in that block. So it is important, right? The dark blue ones are always at the top every time. And maybe this block 2, the light blue ones, tends to have more disease in most cases. So it's like, well, we should account for block in our model. Otherwise, we would it would possibly overestimate the treatment effects there. Okay, so now I'm going to throw some complicated stuff at you late in the day, since we've kind of built up in complexity as we went through the day. Well, you may be getting more and more tired of information, but that's kind of the catch-22 here. Basically, what we're going to do is we're going to fit a model to look at the chance of getting the disease or being healthy as a function of fungicide treatment, as a function of time, and as a function of the interaction of treatment and time, with a random intercept for each block. As we showed, the blocks kind of are different. And the response variable, since we have one column in our data for number of plants and another column for number of healthy plants, the way you do this is you set up the response variable. The first one is the number of healthy plants, and the second is the number of not healthy plants, which is the total minus the healthy plants. Right? So it's like it's called number of successes and number of failures. So that is the number of successes is this column n healthy, and the number of failures is the total minus the healthy plants. That's the number of diseased plants. And we have a random intercept for each block. So that's kind of the main part of our model formula that we're going to put in our GLMM model. Now here's the part that gets a little confusing. We need to look at, there are many different ways to model the relationship of multiple data points from the same plot in time. We can model it in a way that uses a lot of parameters, which is the unstructured covariance. That means for every pair of time points, we estimate a separate correlation between them. There's only 3 time points here, so there's like 3 pairs of time points. There's 3 parameters there. There's also a simpler model called compound symmetry, which means that the correlation between any 2 time points is the same. And there's first order autoregressive. Some people call that AR1. You may have seen that before. That means every time point is correlated with the one immediately before it in time by the same amount. And so unstructured has more parameters. It can fit the data more closely, but it can also overfit because it has so many parameters. And these two, compound symmetry and first order autoregressive, are simpler, but they're less flexible. So we can try to fit them all and compare which one is the best fit. That's what we're going to do. They all have very similar formulas. Unstructured US is the name of the covariance structure function. Compound symmetry is CS, and AR1 for the AR1, the first order autoregressive. And we're gonna fit this 0 plus time, which means we're gonna fit the covariance for the slope over time, grouped by the combination of fungicide and block. So for every plot that's our plot. So for every plot, we have 3 time points, and we're going to add this model term to say how are those measurements correlated. And we have 3 different ways of doing it, and we're going to compare them all.
But then what is the 0 for?
Yes, that means that we are not we have a random. So yeah, I'll show you here in the model formula. We have a random intercept for block and we have a correlation, a covariance structure for plot, which includes the trend over time, but it does not include an intercept. You can't, yes, we can't include the intercept in that. So we have to specify 0, which means exclude the intercept from this formula. We are just fitting a random, an error structure for the trend over time, not for the intercept. The intercept is already accounted for by this block term, basically. Does that make sense?
Yes, yes. Got it.
Yes. So all these formulas are the same. They have the response variable is the number of healthy plants and the number of diseased plants. The fixed factors are the fungicide treatment time and their interaction. We have a random intercept for block, and we're modeling the repeated measures within plot over time. Just 3 different ways: unstructured with a lot of parameters, compound symmetry, which has 1 parameter, and autoregressive, which also has 1 parameter, but has a different assumption about how the time points are related. Other than that, we have the same data and the same binomial response family every time. And we're using the GLMMTMB function, which lets us fit these mixed models with special error structures. So let's go ahead and do that. So I've left it all blank kind of in the first one, but giving you more of the information in the second one. So cbind means combine the 2 columns for our response variable. The number of healthy plants is our number of successful outcomes, comma, the number of total plants minus the number of healthy plants is our number of unsuccessful outcomes. The fixed effect is fungicide, is the first one. Our time point, the interaction, fungicide, time interaction. We have a random intercept for block. And then we have unstructured covariance, US. 0 plus time is our which model term is getting that covariance structure, and which group is it? It's the fungicide block. So treatment within block. That means each individual plot has its own correlation. And we're going to use a binomial response family. So that's kind of a lot. Again, you can go to the worksheet with all the blanks filled in and copy from there if you didn't get all of that. That's the unstructured covariance. So let's go ahead and run that. And so, yes, we get a convergence problem. That means, usually that means, just like the singular fit we saw before, that the model is too complicated for the data set that we have. And I'm not surprised by that, because we knew the unstructured covariance has a lot of parameters and is probably going to overfit the data. So usually I wouldn't even try this, but I'm just showing you to compare and contrast with the other ways of doing it. So let's try this compound symmetry one, which is a little simpler. It has the same response variable, the same fixed effects. We're also going to have a random effect of block, random intercept, but this time we're going to use the CS function for our error structure. Again, by time, the repeated measures are over time. And we also still have the, we still have the binomial response function, because we have, or response family, because we have binary data. So we'll run that, Control Enter. So that ran, and it did not give us any warnings about convergence, because we fit a simpler model with less parameters. That's going to be easier to fit. The AR1, we'll try that as well. We'll see it has the same response variables, the same fixed effects. Block is our random intercept still. We're going to use the AR1 function for the error structure. Again, it's over time. And other than that, everything's the same. So the only difference between these, basically the only difference at all between these three lines of code is this US, CS, and AR1. Other than that, they are exactly the same. We'll hit Control Enter and run this one as well. And it ran without any warnings. That's good too. So let me go back to the slides and see what we're going to do next. As I mentioned, the unstructured covariance model does not even converge. If a model doesn't even converge, we should not use its output for anything. It just didn't give the correct answer at all. So we should just ignore that one. And the other two converged. So we're going to use that same simulated residual approach I showed you a minute ago to look at the residual diagnostic plots for the two models. So we're going to simulate the residuals and then we're going to plot them. So we use the simulate. Yes, we are getting close to being done. I think we'll finish more or less on time or just a few minutes behind schedule. So yes, you can see from the scroll bar here, we're almost done with this lesson. So we'll just knock out the last little bit and then wrap up for the day. Thank you for your patience. We'll simulate residuals and we'll plot. And so the residual diagnostics all look good. We see the residuals going on a straight line between observed and expected, no significant deviations, and there's no trend in the residuals either. Those lines are all flat. And that was the compound symmetry model. Let's do the same for the AR1 model. And again, we see no issues. So we are fine with either of these models. Now let's compare which model is a better fit to the data. Again, as we did earlier today, we compared models with AIC. That tells you how well the model fits the data, and it penalizes models that have too many parameters. And a lower AIC means a better fit. So we'll compare the two models, the fit CS and the fit AR1, with the AIC function. AIC and fit CS and fit AR1. We'll run that. And the AICs are almost identical. They only differ by one. They are. You can also do a likelihood ratio test to get a p-value for the difference associated with the difference between these AICs. If you use the ANOVA function, I'll just type that in there just to show you, even though I don't have it in the slides. We can use ANOVA, fit underscore CS, and fit underscore AR1. And it gives us a chi-squared test, and the p-value is not significant, meaning that there's no real difference in how well these models fit the data. They both fit the data equally well. And so we could really use either one. I'm going to go ahead and use the AR1 model just because its AIC is a tiny bit lower, but there's no practical difference between them. So the last thing, the last set of things we're going to do is actually use this model to make predictions and compare the means of the different fungicide treatments over time, since that's kind of what we're interested in. And again, we're going to use EM means function for that, just like we did in previous lessons. And so we're going to use this fit AR1 as our model fit. We're going to take pairwise comparisons between each fungicide. We're going to use type equals response to get them on the probability scale, get them back in the between 0 and 1, and we're going to use a Tukey adjustment, Tukey test to compare the means. And this is averaging over the 3 time points. So this is kind of ignoring any interaction with time. If we wanted to compare the treatments within each time point, we use the exact same code except fungicide grouped by time, fungicide pipe time. So this is fungicide comparisons averaged over time, 3 times. This is the fungicide comparisons within each time. And every time we're going to do pairwise comparisons and get the p-values every time. So we want the EM means of this fit. This first one is going to be pairwise by fungicide. We want the pairwise comparisons for between each level of fungicide. Type equals response. And we use the 2-key adjustment. Hit Control Enter. Again, it tells us we are ignoring the interactions with time, but I'm just doing this to show you. So if we type EMM _fungicide fung into our console, we can see what we got. Here are the probabilities averaged over the time points. You can see the probability of having healthy plants is, the model is estimating it to be 73% for the control and a tiny bit higher for the other treatments, 79, 77%. So these fungicides are not magic, you know, they're only making the probability of disease go down a little bit. And here are the odds ratios comparing them. So like this DACD is significantly decreasing the odds relative to the control. The odds ratio is 0.7, so the odds are 0.7 times as high of or 0.7 times as high of getting disease if you have DADC fungicide versus control, for example. And we can do this by time point as well. The only difference in this code here is we have fungicide by time. Hit Control Enter to run that. And we can type the name of that into our console and see what it looks like. So again, we have a lot more output, right? Because here are the probabilities at each time point. The probability of healthy plants is around 80% for all the treatments at time 12. It starts going down a little bit as time goes by. And here are the pairwise comparisons with p-values for all the time points for each pair of treatments. But just like I go back to the slides here. Yes. Oh, this is, I should have put this earlier. This is the slide for the odds ratios where I was wanted to explain this earlier, but the again, the odds ratio of 1 means no difference. Odds ratio less than 1 means lower odds of the first one than the second one. So like if the odds ratio is 1/3, that's like 1-to-1 odds versus 3-to-1 odds. 50% versus 75% probability has an odds ratio of 1/3, for example. And again, because we had so many p-values, even though 0.05 is just a threshold, we can summarize with the letters and look at, we can do that with the CLD function, just like we did before, and use the 2-key adjustment, and this will give us our letters. And then this is the last bit of code that the EM means from the EMM fungicide. We're going to get the multiple comparison letters for that. We're going to use the 2-key adjustment for it. And we're going to do the same for the fungicide by time. Oh yes, and we'll use the CLD function here. So once we run that, that'll give us our letters. And this gives us a note that the confidence interval adjustment was changed to a different adjustment, but that's kind of a routine message. And yes, so if you look at the CLD of fungicide overall, you can see that there are some statistically significant differences in the probabilities averaged over the time points. And if you look at it within each time point, you can see that there's at the early time point, there is no significant difference because the disease hasn't had as much time to progress. So the effect of the fungicide is not as obvious. But then at later time points, we see that this DACD does have a significant effect relative to the untreated control, but the other two don't. And the last thing I wanted to show you, I'm not going to go through the code for it, but I made a plot that shows the means with confidence intervals and error bars with the letters on top of them, so you can see, just kind of visualize the results a little bit better. So I'll just run this code to produce that plot. And this is it. So these are the probabilities of having a healthy plant with the multiple comparison letters on top at each time point and overall. So this panel has the overall probabilities. So you can see exactly what we saw in these tables here, that there's no significant difference at the early time point, and then it is shown over time that there's a difference. Is there a question? All right. So yeah, and this is just I'll wrap up here real quick since we're now done with our time. This is our the SAS equivalent code for what we just did in R. I provided that for anyone who knows SAS and wants to see more or less how to do the same thing we just did in R and SAS. And yeah, so that's all I have for you today. I think we finished more or less on time, which is great. And for those of you who stuck it out to the end, thank you. And hopefully you learned a lot and can be proud of yourself learning about generalized linear mixed models, what they are, how the link function works to translate between the data scale and the model scale. We learned about repeated measures. We learned about binomial data. We learned about error structures and how to use these very powerful and cool models to make predictions. And yeah, so pat yourselves on the back. Well done.